So let's recap what merge sort does. Right? Here's merge sort. Split along the divide and conquer framework. So 1, we split array in half. Okay, so this is fast, right? This is a constant time operation because all we have to do is find the middle index. Right? So this is constant time. 2, then we merge sort both halves, right? So MS for merge sort both halves. Right? We trust that whatever comes up is sorted, and so then once that's done, we go and merge those two sorted arrays back together, right? And so in step 3, we merge the sorted arrays. Okay, so there's a 2t of n over 2 happening here. And then when we merge the sorted arrays, we just showed that that's a linear time operation. Okay, so in some sense, what you can do is you can look at merge sort and you can ask the question, where's the work happening, right? What about merge sort is slowing it down? There's not much that, with this basic architecture, there's not much we can do about this. But we might ask the question, how could we improve this, right? How could we make the merging faster? Because that's where all the work is happening, right? Merge sort is fundamentally a linear time algorithm that is executed a logarithmic number of times, right? That's what merge sort is, right? That's exactly the way to think about it. It's a linear time operation or algorithm that is executed logarithmically many times. Okay, this is merge sort. The logarithmically many times comes from the recursive piece here. Anyway, all the work happens in step 3. So, you know, what we could ask, is there a way that we could offload the work from step 3 onto step 1? Okay, so let's just imagine, and we're just playing algorithm architect at this point, right? We're not writing an algorithm, but we're just thinking about what it would look like if somehow we could get 3 to be fast. So let's just imagine a new algorithm, a new sorting algorithm, and I'll call this new algorithm new sort, right? Just for fun. So imagine new sort. Okay, and what new sort is going to do is first, it's going to split somehow, right? Split somehow with some complexity, right? We don't know yet. We haven't determined what that needs to be. Then it's going to new sort both halves. And so we'll have a 2t of n over 2, just like in merge sort. And then we're going to try to have split in such a way that when we merge, we can do it in constant time. Right? So here's the question going forward, is what does the split have to look like for the merge to be able to occur in constant time? And then we'll merge somehow in constant time. Okay, so the question is, what kind of split would allow a constant time merge? Okay, well, let's think a little bit about what merge sort is doing in its merge. Think about why it has to be linear time, right? So let me write down a couple arrays. So here's 1, 2, 3, and 5, and 4, 6, 7, and 8. So here's 2 sorted arrays that we're passing to merge, to the merge function. And the question is, you know, what about these sorted arrays causes merge to be slow? So what merge is going to do is it's going to look at these 2 elements. It's going to compare them and say 1 is less than 4, so we'll copy 1 in, right? So 1 goes in. And 1 just goes directly in. And then it looks at 2 and says, 2 is less than 4, so 2 goes in. Then it looks at 3 and 4 and says 3 is less than 4, and 3 goes in. Then it looks at 5 and 4, and now 4 is less than 5, right? So it has to take 4 and drop it down here. And then what it does is it looks at 5 and 6, and it says 5 is less than 6, so 5 goes here. And then the first array is empty, and so it just gets to bulk copy the rest of these down. Okay. So assuming that that bulk copy is fast, which it certainly can be faster than having to compare a whole bunch of numbers, you know, the reason that this merge was slow is that we had to check all of the elements of one of the arrays, of at least one of the arrays, before we were sure that there were no overlaps. Right? The fact that there was an overlap between these two arrays made it slow. Right? So the idea here is essentially if B and C, so I'll call this array B, and I'll call this array C. If B and C overlap, right, in the sense that the largest element of B or the smallest element of C is less than the largest element of B, if they overlap, then we have to check at least every element of at least one of them. And we might have to check all the elements of both, right? But at least we have to check all the elements of one, which makes this a linear time algorithm, no matter what we do, right? If B and C overlap, we have to check all of one of the arrays to make sure that we're creating a sorted array in the output of one array to be sure we're getting it right. Output is sorted. All right. So what would we have to do to get around this? Well, we'd have to ensure that B and C have no overlaps. Okay. So if our question here is what kind of split in this step would allow for a constant time merge, one possible answer is that the split would have to have no overlaps. Right? We would have to have a guarantee that all of the elements in the left array are less than all of the elements in the right array. So if we can do such a thing, then we can get away with a constant time merge. Okay. And so the picture then is, suppose we had 1, 2, 3, 4, 5, 6, 7, 8, right? If those were our two input arrays, and somehow we knew that 4 is less than 5, right? If we knew that 4 is less than 5, then we'd have a constant time, we'd have the ability to do a constant time merge, right? Because we could just bulk copy all these into the first 4, and then bulk copy all these into the last 4, 6, 7, 8. And if we could do this in place, then we wouldn't even have to do the copies, and it could be even faster. Okay, so here's our goal. Our goal is to come up with a way of splitting an array into two different pieces, such that all of the things on the left side of the array, or in one piece, are less than all of the things in the right side of the array. So split in such a way, and I'll say split into B and C in a way that B, and I'll just say n minus 1, the last element of B is less than or equal to the first element of C. And I should even say not this. I should not even say this. I should say such that BI is less than or equal to CJ for all I and j. Right? No matter what indices I plug into these, everything in B is less than everything in C. Okay. And so this is our goal. Our goal is to figure out a way to do this split, because if we can split in such a way that this is satisfied, then we'll be able to merge in constant time. And so really the question ends up being, is it possible to do this kind of a split in linear time? And that's what will lead us to our next divide and conquer themed sorting algorithm.